Hello everyone, we are going to start section 8.2 today, talking about compositions and inverse transformations for general linear transformations. We're going to start with definition. Transformation T is called one-to-one if it maps distinct vectors from space V into distinct vectors in space W. For example, I'm going to draw the picture and then write down the formula. So for example, if you have like vector 1 and vector 2 into v1 and v2, then transformation maps them into two different vectors, w1 and w2, and they are going to be not equal to each other. So I'm going to write it down as a formula. So So if vector v1 is not equal to vector v2, and these vectors belong to space V, then transformation of v1 is not going to be equal to transformation of v2. And these two vectors, this one and this one, they belong to space W, and they are like W1 and W2. So the results of transformation or images are not equal to each other if originals are not equal to each other. Example of bad transformation. So this one, let me label it. This transformation is 1, 2, 1. This one, this transformation. Now, the bad transformation going to be in red. We have these two circles and vector v1 and vector v2. And they go into the same vector w. Then this transformation is not 1, 2, 1. Because v1 is not equal to v2, but t of v1 is equal to t of v2. Well, the result of transformation is going to be just the same vector. Well, again, this is going to give us an idea how to check whether transformation is 1-to-1 or not 1-to-1, and what happens when it's not 1-to-1. So a transformation like this is not 1-to-1. You're probably familiar with the idea not 1-to-1 from functions, right? If a function is kind of like a squaring function, for example, it squares -2 and 2 and give you same result 4, means that it's not 1-to-1. Okay, and that was the first definition. A second definition. One more. Definition 2. Transformation T from V to W is onto if any vector from W is the image of at least one vector from V. Okay. Well, going to probably draw two pictures showing one is onto and one is not. First, onto. So it's space V, that's space W. So the vectors from V go to vectors from W, and actually they take the whole space. So range of transformation equals a whole space W. That's onto. It's not necessary that onto transformation must be 1-to-1. So actually you can have two vectors from V going into the same vector into W, because they're telling that it's supposed to be at least one vector, but no one tells that only one vector. So you can have actually 5 different vectors going into same vector into W. important is that all vectors into W are going to have something in the back, original. All images are images of something. All vectors in W are images of something. And this is onto, right? And not correct example, not onto. This is V, and this is W. And transformation of V goes like this. So this shaded area is range of transformation. Well, I did not label that it was transformation T here also. So what does it mean, guys? This is not on to. I'm going to put it in parentheses because it just onto looks like just a word. So we do have some vectors in W which do not have anything here, nothing here. They don't go into V. So, well, happens sometimes, right? So transformations like this are called not onto. We are going to consider some examples. But before we do examples, I want to prove a couple of interesting theorems. Before we do examples, okay? Theorem. Transformation T from V to W is 1 to 1 if and only if and only if, and this sign means that if and only if, a kernel of transformation is equal to 0 vector. Well, what does it mean, guys? Well, you know that any transformation, any linear transformation transforms 0 vector into a 0 vector, right? The theorem tells that if transformation is 1 to 1, no other vector is going to be transformed into 0. Remember, what is kernel? Kernel are all vectors which are transformed into 0. So 0 is always there. But if it's 1 to 1, there is going to be nothing else in. I'm going to prove it. It's a kind of really, really easy proof. So, proof. I'm going to do this direction. So what is given? Given T is 1 to 1. Need to prove kernel equals 0 vector. How I'm going to do it? Well, if transformation is 1 to 1, I'm going to draw the picture. V and W. And imagine that, assume that kernel of T has some other vectors. Well, at least one other vector, some other vectors. For example, U, which is also belongs to kernel of T. Well, we know that is 0 belongs to kernel of T, but maybe there is other vectors which belong to kernel of T, like U. What do we know about that U? Well, if it belongs to kernel, means that transformation of U must be equal to 0, right? We also know that transformation of 0 is equal to 0. We proved it somewhere in the previous. So we do have two different vectors, U not equal to 0, because if they're equal to, then there we have nothing to prove. But they go into the same vector 0. So transformation of U is equal to transformation of 0 equals to 0, which means that, which contradicts the idea that T is 1 to 1, because if vectors are not equal, their transformations must be not equal. Contradiction to idea that T is 1 to 1. So we did the proof. I'm trying to draw that. We know that 0 always goes into 0, but if we do have some other vector u, which also will go into 0, is it possible? Well, we do know that this picture is not possible for one-to-one transformations. I specifically was showing that. Okay, we proved the first part. The second part. Proof of the second part. Given kernel of t equals 0. Need to prove guys, I'm going to erase this and put it lower because here is a need to prove t is 1 to 1. Okay, well, again, we are going to start with assumption. Assume t is not 1 to 1. Then we have u1 not equal to u2. Sorry, started writing down v to u2, for which t of u1 is equal t of u2. This is just like negation of the statement of 1 to 1, right? So if like we have two different vectors going into the same vector in W space. Now guys, what I'm going to do, since u1 is not equal to u2, I'm going to build a difference between them. u1 minus u2. Well, because they are not equal to each other, the difference is not going to be equal to 0. Just if they are equal to each other, we subtract them and we get 0. If they are not equal, difference is not 0. I'm going to apply transformation to this difference. Transformation of u1 minus u2 is going to be what? First, I'm going to apply like the theorems we proved about transformations, that I can actually consider it as a difference of two transformations. Now, what is transformation of u1 and the transformation of u2? Well, because they are equal, I'm going to write down t of u1 minus t of u2 equals to 0. Just because they are equal, from this follows this, which means that the difference between them is going to be 0. So what I see a transformation of some non-zero vector goes into 0, and it contradicts to what? The statement that kernel, let me write it in words, contradicts to the statement that kernel of t is only 0, right? Means that there is some other non-zero vector which will go into 0, into this 0. Well, basically it contradicts to what is given. Okay, well, kind of a simple proof, but a nice one. Okay, well, why do we actually need these one-to-one transformations? Usually, guys, if you remember, for functions, we need them to introduce after that inverse transformation, right? I'm going to maybe kind of consider a couple of one-to-one transformations, and maybe should just introduce inverse transformation. So let me give maybe an extra definition. If linear transformation T V to W is 1 to 1, then we can define inverse transformation T inverse from W to V. And cancellation equations are going to work, right? So if you apply T inverse to T of V, you're supposed to get back V. I'm going to draw the picture for inverse transformation. So it mentions that we have 3 It's W, and transformation is 1 to 1, which takes vector V, transfers it into T of V, and inverse transformation. Inverse transformation, T inverse, is going to bring back this resulting vector into V. And also remember there are two cancellation equations. Second cancellation equation is T of T inverse of, well, I'm going to label it a W. This vector is W, okay? W is going to be equal to W. So if you apply it in opposite directions. Let me introduce maybe a couple of transformations which are like 1 to 1 and have inverse. Well, remember when we were talking about matrix transformations, we had transformations with invertible matrix. When you do transformation from Rn to Rn, and if this transformation is 1 to 1, if matrix A, maybe I should write a matrix because it looks like A, just a letter, is invertible. Well, again, why it's going to be like invertible matrix is going to produce matrix transformation. If we kind of remember that matrix transformation TA of vector x is actually going to be A multiplied by x. And if we define actually T inverse of A, well, of x, or like, let's still x, okay, as A inverse of x, we are going to have these cancellation equations working, right? A x, A inverse is going to be identity by x, or kind of the same vector x. So, well, what else we can have, like, let's say, one-to-one transformations. Another example of one-to-one transformation. Let's imagine that we have two-dimensional matrices and we transform them into R4 by next transformation. Take matrix and do it A11, A12, A21, A22. So we transform it next way, transformation of, let me use M here. Transformation of M is going to be A11, A12, A21, and A22. Also going to be one-to-one transformation, and it's going to have an inverse. Okay. Well, basically, guys, a very good idea if you want to check if transformation is one-to-one, going to be check the kernel of transformation. Let me give you example of not one-to-one transformation. Example number 3. So remember we had this orthogonal projection. Well, for example, projection on x-axis. We have a vector and projection is going to be, so that's vector x, for example, and this is transformation of x, projection on x-axis, right? What is kernel of this transformation? Kernel of this transformation is going to be like a whole set of numbers with x coordinate equals 0 and y kind of any number. So we're going to have a kernel. It's a whole line over here, right? So it's not equal only 0 vector. So we're going to say that it is not one-to-one. So kernel of this transformation, because it has more vectors than just 0 vector, is not one-to-one. I'm going to label projection. So the good idea to check what is kernel of transformation. If it's not just zero vector, well, probably it's going to be not one-to-one, according to our theorem. Well, okay. So we already introduced one-to-one, and I used already the idea of composition, but I did not really introduce composition of like two transformations. Maybe I should introduce it before I do that idea. Okay, definition number 4. If we have two transformations, T1 linear transformation from U to V and T2 transformation from V to W. Then we can define a composition of two transformation, T2, T1, U, which is going to be just application of two transformations in like order. Composition. I'm going to draw the picture, but generally speaking, we already have seen this picture so many times. So that's space U, space V, and that's space W. So my first transformation is T1, and my second transformation is T2. And you start with a vector over here, little u, and you end up with vector over here, w. So transformation is just application composition is just application of one transformation over another one. Let's kind of do example of compositions. Example. Let's consider transformation 1, x, y, two-dimensional space are going to be just multiplication x coordinates by 2 and y coordinates by 3. Transformation 2, two-dimensional space, is going to do x minus y and x plus y. Well, these are just the formulas for transformation. So how the composition is going to look? Composition of T2 over T1 applied to xy. Well, I'm going to put T2 over here and first kind of take xy and apply first transformation. 2x, 3y. Now my new x is 2x and my new y is 3y. So I'm going to plug them here, here, and here, and here, and get a composition. So it's going to be what? 2x minus 3y and 2x plus 3y. And that's going to be my result. So that's how composition is going to look. What is going to happen if we have composition of one-to-one transformations? So composition of one-to-one transformations. I'm going to draw the picture first and then kind of show the formula. So imagine that we have two one-to-one transformations. I don't know, let's do U, V, W. Transformation T1 and T2 are one-to-one. So what is going to happen? Well, if each of these two transformations is one-to-one, we can, if transformation is one-to-one, we can define transformation which is going to be inverse of T2 and inverse of T1, right? So, and we see that we can actually travel from here, from vector little w, over here to vector u here. And kind of do backward road. How we do it? We first apply T inverse of 2, right? And I'm going to put W vector here. And then we apply over it T inverse of 1. And that's going to be a composition of T inverse of 1 over T inverse of 2, right? And what is going to be? We are going to call it, this like the whole green thing, as inverse of composition. So if we had original transformation T1, T2, that's original. Then inverse transformation of this T1, T2 inverse is going to be equal T1 inverse by T2 inverse. Guys, do you see that we are using basically very same rule we had for matrices, right? If you have a inverse of like a product of two matrices, it's going to be actually product of two inverses in opposite, in reverse order. Well, obviously it's going to work for matrices, right? Okay. Well, maybe we should consider a couple of examples just to figure out if transformations are one-to-one or on-to. I explained a lot about one-to-one, but I did not explain a lot about on-to, right? Well, let's just kind of scroll it up and do a couple of examples. For both examples, the question is transformation one-to-one? Question number one, is transformation too many lines here? Don't like it. Onto. Okay. Well, I'm going to consider, first question is going to be transformation of two-dimensional vectors into two-dimensional vectors by the formula. Question number two, transformation of two-dimensional vectors into two-dimensional vectors by the different formula. Both are transformations of, I would say, R2 to R2. This one is also R2 to R2. And we will try to answer the questions about like kernel and like not kernel, but about one-to-one or on-to. Well, let's talk about the first problem. Is it one-to-one? I'm going to solve the first problem. Well, I'm going to use my advice about kernel. Kernel tells, like the kernel theorem tells that T is 1-to-1 if kernel of T is equal to 0. Let's find actually kernel of this first transformation. Remember that kernel are all vectors which transformation turns into 0. So what are going to be all vectors x, y, which are going to go into 0, 0 vector? Well, let's write it down. 0, 2x plus 3y. So for which x and y, actually we are going to have the second 0. First 0 we are going to get automatically, right? Going to write down 0 equals 2x plus 3y, from where y equals minus 2x over 3. So actually we are going to have a bunch of vectors. For like given x, you are going to get a y. For example, let's use x equals 1, then y is going to be minus 2 over 3. And this vector 1 minus 2 over 3 belongs to kernel of T, y. Because actually if you apply the formula for it, it's going to be transformed into 0, 0 vector, belongs to kernel. So I'm going to make conclusion that t is not 1 to 1 because of this, because kernel is not equal. Kernel of t is not equal only 0 vector. It also has like some other vectors and actually many other vectors, okay? Okay, very good. So first transformation is not 1 to 1. Is it onto? Onto means that every vector in image space has something back. Well, let's just look at this. So I'm going to actually show that t is not onto. Why? Let's pick up a vector from R2. For example, let's pick up vector W with coordinates 1, I don't know, even 0. This vector belongs to R2, and that's going to be our W, space of the image, right? Does it have anything back? Does it have anything back in like original space, this one, or space V? Well, because all vectors from V are going to have x component equals to 0, and ours has 1, this vector doesn't have any, like, no vector from V is going to produce this vector by our rule, of course. So t of any xy will never be equal 1, 0. It will be equal 0 to x plus 3y. So you can turn this one into 0, yes, but you cannot turn 0 into 1. Well, not that transformation is not on 2. Okay, so we are done with our first problem. Second problem, transformation which do x plus y and x minus y. Okay, I'm going to scroll it up and just copy the problem so we can transformation of xy, which is doing x plus y, x minus y. And it's going to take R2 and transform it into another R2 two-dimensional space, right? So this is V, this is W, and we're going to start, of course, with like checking 1 to 1. What is kernel? Which x and y from here are going to produce 0, 0 vector over here? Because these are going to be x and y in kernel. I'm going to set up x plus y equals 0, x minus y equals 0. So basically to produce 0, 0 vector, I'm supposed to satisfy these two equations. Well, if I add these two equations, I'm going to have 2x equals 0, which means that x must be equal to 0. And if I plug x equals 0 here, I'm going to get y equals 0. So actually, the only one vector in kernel of this transformation is 0 vector. So I'm going to write down that kernel of this transformation is only vector 0. In our case, it's going to be actually like vector 0, 0, right? If you literally show what vector. So only x, y equals 0 are going to produce 0 here. So I'm going to make a conclusion that t is 1 to 1. This transformation from problem 2 is 1 to 1. Is it onto? Onto means that like any vector from this space, any vector from this space is going to have something back here, something which is producing this vector. Well, to check it, we again will need to solve system of equations. Let's write it down. So let's imagine, I'm going to put on to. Let's imagine that vector which belongs to this space has coordinates a and b. It's two-dimensional vector. Like all space, we can be represented with a pair of two arbitrary numbers, a and b, right? Well, is it like, will we be able to find x and y which produce any a and b? Well, I'm going to kind of write down that t of x and y is going to be equal x plus y, x minus y, and it's supposed to be equal a pair of two arbitrary numbers. This pair belongs to this one, and this pair belongs to this space. Well, so I'm going to have two equations, x plus y equals a, and x minus y equals b. If I can find x and y for any a and b, if I can, which are like, I'm going to prove that, like for any a and b, there is going to be some vector which is producing them. Then, yes, it's going to be on 2. Okay, so I'm going to do, like, add these two equations. 2x equals a plus b, from where x equals a plus b over 2. Now, I'm going to subtract my second equation from the first one, and I'm going to have 2y equals a minus b, from where y equals a minus b over 2. So guys, you see that like every vector a and with coordinates a, b from my resulting image space is going to have something in the back, and this actually something in the back is going to have coordinates x, y equals a plus b, a minus b over 2. So I'm going to write down it is on 2. So any vector from here with coordinates a and b is going to have something which is producing this vector, and that something is actually going to have coordinates a plus b over 2, a minus b over 2. So every vector here. Well, it's on 2. Well, that's it. We considered the second problem. So the first transformation was neither on 2 or 1 to 1. A second transformation is actually both 1 to 1 and on 2. We are going to have some special name for transformations which are 1 to 1 and on 2 at the same space. We are going to call them isomorphism, but we are going to talk about isomorphism in our next lecture. That's it for today.